Hello everyone! So once again, we are looking at our next lesson. So we're looking at 7.3 today. This will be the last lesson that you'll have for the week. What we're looking at first on this is determining the angles of rotational symmetry, as well as the number of lines of reflective symmetry for each of the polygons below. Now, we've talked a little bit about the rotational symmetry, where we take 360 and divide it by the number of sides. Now, that only works with regular polygons. So these first three that we can see right here, these, well, specifically the rectangle and the rhombus, these are not regular polygons. So as a result, that means we can't use our rule 360 divided by the number of sides to take and solve for the rotational symmetry. But the rest of them, the equilateral triangle, the regular hexagon, the square, and the regular decagon, those are all regular polygons, which means you can use 360 and divide it by the number of sides to find your rotational symmetry. All right, for the line symmetry, so the lines of reflective symmetry, that just means think back to when you were young. If you fold it in half, do the two sides look the exact same? Or if you cut it down the middle, do you have two congruent pieces? That's what we're looking at there. So how many lines of symmetry there are. So if we look at my handy dandy slide here, first thing we're going to look at is the rhombus. So the rhombus, like I said, is not a regular polygon. So the 360 divided by n won't work for the rotational symmetry. The line symmetry, we have to think about cutting this in half. So if we look at that figure, how are we going to cut this rhombus in half? Can we do it vertically? Not going to work. It's not going to look the same. What about horizontally? Nope, it's not going to work out. But if we cut it on the diagonal, bear with me, my line obviously is probably not going to be the best looking line, but if we cut it diagonally like so, if it were a perfect line, would that cut it in half? Would it look the same? Yes, it would. So the diagonals are two lines of reflective symmetry for this rhombus. So there are two lines of symmetry for this figure, so make sure you get two wrote down on that one. And then for the rotational symmetry, well, how much are we going to have to rotate that rhombus so it looks the exact same? Obviously, 360 degrees will work, but will 90 degrees work? No, sadly, it won't work. What about 180? Yes, 180 just takes and flips end for end to get us our new figure. So 180 degree rotational symmetry. So once again, number 3 has 180 degree rotational symmetry. Alrighty. So for those regular polygons though, there is a handy dandy little trick for how we take and do those. So looking at them down here, let me pull this back up. The rules, we already know the rotational symmetry. So rotational symmetry, we take the 360 and divide it by the number of sides. But for line symmetry, rather than actually having to figure out all the different ways you can cut it to make it look the exact same or fold it to make it look the exact same, the number of lines of symmetry in a regular polygon, only a regular polygon, is the number of sides the polygon has. So if we have a 5-sided regular polygon, we have 5 lines of symmetry. If we had a 10-sided regular polygon, we would have 10 sides of, or 10 lines of symmetry. So that's a nice little thing to know about with our symmetry. It makes it very, very easy to take and work with. So just knowing the number of sides for a regular polygon will tell you the number of lines of symmetry it has. All right, so like I said, this should be a decent review. We've done this in the past. You guys should know this, All right, the next thing we're looking at, you definitely will know this. We're solving the triangle. We're finding all of the missing information. So notice we have one of our sides. I will tell you, these are all right triangles, even though it doesn't show the lovely right angle box, but they are all right triangles. And we have one side and an angle measure. So how do you suppose we're going to solve for these? You got it, SOHCAHTOA. So if we look at SOHCAHTOA on this first one, remember a nice little refresher since it's been a while. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So remember, The hypotenuse is always across from the right angle, so the 1 would be our hypotenuse in this case. And then depending on our angle of reference, which since we have the 60, we'll use it as our angle of reference, opposite is the side across from it, adjacent is the side next to it. So we need to take and solve for both x, y, and z. Now, I will tell you in this one, solving for the angle is the easiest one to solve for because all we have to do is take 180, because that's how many degrees there are in a triangle, and subtract our 60 and 90 from it. So 180 minus 60 minus 90, well, that's going to give us 30. Excellent. So z equals 30. Wrong direction, sorry. So let me make this bigger. There we go. Okay, so now finding our sides, I'm going to solve for x first. So using 60 as our angle of reference, x is opposite, and the 1 is the hypotenuse. So we're going to use sine. So sine of 60 equals x over 1. So to solve for this, we multiply both sides by 1. That cancels out, remember. So we have 1 sine of 60 equals x. So now, remember, take out your calculator. You can use the ones on your phone. We tested this out a bunch during class. Remember, you have to have it unlocked so you can take and turn it to the side. So type in your 60, then hit the sine button. We get that big, long, crazy decimal. Multiply it by 1. So in this case, it's going to stay the same. So our solution is 0.866. So that means 0.866 equals x. So that's our side length there. All right, so now we have our x side. Now we're going to go to our y. Now, we could use the Pythagorean theorem, but because we rounded and did an estimate on our x, we don't want to take and use that value to plug into the Pythagorean theorem because it's going to be a little off. And remember, rounding kills people, so we don't round. So for y, we're going to set it up. Y is our adjacent side because it's right next to the 60, and we have our hypotenuse. So this time we're going to use cosine. So cosine of 60 equals y over 1. Multiply both sides by 1. That cancels out. So 1 cosine of 60 equals y. Once again, go to our handy-dandy calculators on our phones. Turn it to the side. Type in 60 and then cosine. We get 0.5. We multiply that by 1. It's going to be the same thing. So we get 0.5. So that means y is 0.5. So we have now solved our triangle. We know all the missing sides and the missing angle. So remember, SOHCAHTOA is what you're going to be using on 8, 9, and 10 to finish solving those. Now on 10, you will be able to use the Pythagorean theorem to find the other missing side, but to find both the angles, you will have to use sine, cosine, and tangent once again. And remember, when we're solving for angles, we use the inverse sine, inverse cosine, or inverse tangent. So remember, use those other functions. So don't use the regular sine, cosine, and tangent, or you'll get the wrong things when you plug them into your calculator. Okay? So give you a second to make sure you have the SOHCAHTOA and your properties of sine, opposite of hypotenuse, all that wrote down for a quick sec. Okay, so that's what you're doing, like I said, for 7 through 10. I did 7 with you, so hopefully you'll be able to figure out using that how to do 8, 9, and 10. Like I said, 10 is slightly different, but you should still be able to figure it out using the inverse functions. Remember, inverse when we're solving for angles. All right, the next part of this, we're looking at more to deal with circles. Now, up until now, you haven't had a lot of circle things to know. You know about the radius, you know about the diameter, things like that. But now we're going to get into some new terminology and new parts of circles. So we want to find the value of the angle of the angle or the intercepted arc. So the intercepted arc, if we look at this picture here, this arc LN, that's being intercepted by this radius here, LM, and this radius here, MN. So it's cutting into it. It's cutting out that arc from the overall circle. So that's what's known as the intercepted arc. Basically, it's a portion of a circle. Now, when what's intercepting it is based at the center of our circle, so just like LN is, then the angle of the arc is the same as, whoops, didn't mean to do that. The angle of the arc, meaning this curve part right here, that's our arc, is the same degree as the angle inside. So it is the same as that central angle. So angles that are right there on the center of a circle are what's known as, oops, let me find my right side, central angles. So if we look at this, I drew it out so we can take and draw on it a bunch. Like I was saying, for LN, this right here is the intersected arc. When we have the central angle, so an angle that's vertex is the center of the circle, the angle and the intersected arc are the exact same measure. So arcs are going to be a degree measure when we're talking about when we have the arc shown just like this. The measure of that arc is a degree value. And so this little curve, you might be noticing how we have the measure and then we've got LN with this strange curve over the top. This curve is just how we represent arcs in mathematics. So think about it. This is a curve. It's a portion of a circle. That's exactly what that's representing there. So that's just anytime you see that, you know it's talking about the arc and you're dealing with a circle. So it is 110 degrees. Now the next one, it's saying the measure of angle OLN. So OLN is this angle here. So right here. Now, this angle is intersecting to give us the arc of 130 degrees. But the angle here is not 130 degrees. Reason being is, remember, to have them be the same, it has to be based off the central angle. This isn't at the center of the circle. It's on the edge of the circle. So when we're going between the arc and the angle that lies on the edge of the circle, you're going to divide by 2 or multiply by 2. So being as we have the arc, we're going to divide it by 2. If we had the angle, we'd multiply it by 2 to get the arc. So we're going to take 130 and we're going to divide it by 2, which is going to give us 65 degrees. So the angle the angle OLN is 65 degrees. All right, and we have one last arc. We have arc OL. Now, if we notice, arc OL is just the arc that's cut by the chord OL. There's no angle involved with that. But how many degrees are there in a full circle? 360. We know this arc is 110. We know this arc is 130. Excuse me. So we're going to take 360 minus 110 minus 130. Sorry, running out of space. Oops, wrong direction. And when we subtract those three things, we're going to end up with 120. So our arc OL is 120 degrees. Okay? All right, so looking at 14, I want to do a second one of these with you guys just to kind of make sure that you're understanding and getting these, since I know they can be a little tricky and it is some new information that we're dealing with. Part of it got erased. So that is a 5. All right, for this one in the problem, it told us that NK is a diameter of this circle M, and NL had a length of 12, and KL had a length of 5. So that's what I have marked on there. We need to figure out what the length of the diameter is. So we have what appears to be a right triangle here. So we can use the Pythagorean theorem. Remember, Pythagorean theorem is a squared plus b squared equals c squared. So 12 squared plus 5 squared equals c squared. 144 plus 25 equals c squared. So then add these two together, we get 169 equals c squared. To get rid of the square, we take the square root, that cancels. So we end up with 13 equals c. So that means our diameter has a length of 13. Now, we're looking at the measure of arc NLK. So NLK. So it's this whole arc right here. Now, anytime we have an arc that's endpoints are the diameter of the circle, that means we have a hemisphere or half the circle. So what's the degree for half of a circle? 180 degrees. Excellent. Another way to think about that is the central angle here. This forms a line. Remember, lines have 180 degrees to them. It's a straight angle. So that's how we know that it should be 180 degrees. So now for C, the measure of arc NJK, when we deal with arcs, if we're doing a major arc or a hemisphere, we use 3 points to take and name it. If we're doing a minor arc, we use just 2. So a minor arc is less than 180 degrees, just like our LN over here and our OL. Those were minor arcs. Okay? So for this one, once again, if we think about it, we have the other side of the circle, so we have the other hemisphere. So this one's also going to be 180 degrees, since it, once again, is the endpoints of our diameter. All right, our next one, we're looking for angle NLK. So NLK. Well, we said this is a right triangle. That's how we did the Pythagorean theorem to solve. So that means it's 90 degrees. The other way we know this is 90 degrees, it's this angle, endpoints are on the diameter, which means its arc is 180 when we're going from the arc to the angle that's on the edge of the circle that's intercepting it. We divide by 2. 180 divided by 2 does give us our 90. All right, for E, sorry, can't see that. We have the measure of arc KL. So that's this little arc right here. So in solving for this, we have to think about it just a little bit. So with this, we can actually use sine, cosine, and tangent to take and solve for this, because based on what we have, we don't know what this angle down here is, and we don't know what this angle up here is to be able to find these 2 other arcs. So we want to take and use our trig functions. So in searching for this angle right here, we have our adjacent and our opposite. So we're going to use tangent x equals opposite over adjacent. And now remember, when we're solving for an angle, x is going to equal the inverse tangent of 5 over 12. So now we're going to take and plug that in to our calculators. So once again, take out our phones. So remember, do 5 divided by 12 first. We end up with 0.416 repeating. So we're going to take that and turn it to the side. Remember, hit the second, and then you get the inverse functions. Hit the tangent inverse, and we end up with 22.619. So I'm going to say 22.62 degrees. Now, that's not the answer for the measure of KL. 22.6 degrees is just what this angle here is. What this arc is, remember, we're going from the angle to the arc, so now we're going to multiply. So we're going to take that and multiply it by 2, and we'll end up with 45.24. So we multiplied by 2. And that's how we found that, because we're going from the angle to the arc. Going from the angle that's on the edge of the circle to the arc, we multiply by 2. In the reverse, we divide by 2. So same idea for this last one down here. This one we can solve a little easier, taking 90 minus 22.62. 90 minus 22.62 gives us 67.38. So there's our degree for this angle up here. I marked it with a double arc, so this angle right up here. And then to find what this arc NL is, we take and multiply this by 2. So times 2, which will give us 134.76 degrees. So it can be a little confusing taking and figuring out all these pieces, especially when you start getting full-on shapes in there rather than having just triangles and angles. It definitely makes it a little more complicated, but just remember, if the angle that's intercepting your arc is at the center, so it's a central angle, then the arc and the angle are the exact same degree. If you have a hemisphere, your arc is always going to be 180. If you have an angle that is on the edge of the circle and the arc it intercepts, the relationship is either multiply or divide by 2, depending on which value you're given. If you're given the angle, multiply by 2. If you're given the arc, divide by 2. Okay? All right, and one last portion for you guys with this lesson. So let me scroll this on down so you can see. Oops, perfect. Okay, so once again, we are talking about circumference and area. So it's got the formulas right here to remind you what those are for this lesson. Hopefully you guys know them already. So using this, we're going to answer these questions about the circle that we have here. So once again, I have this drawn out, so I'm going to show that on my whiteboard to make things a little easier for me writing. Okay, so what it's telling us is circle R is cut by 2 diameters that are perpendicular, to each other. So what we want to do first is find the distance to walk along the arc NQ. Now, we've been saying a lot about arcs. Arc is your key word for this lesson. So this is exactly how you spell it right here. Arc is your key word. Make sure to make note of that and remember to submit it on Canvas for credit. Remember, it is part of your grade. Okay, so what we want to find is the arc NQ. NQ is this right here. Now, we talked about how arcs are part of what's going around the circle. So how do we find the distance around the whole circle? Well, we use circumference. So using our formula, C equals 2 pi r, we're going to solve for that. So we know our radius is 6. So C equals 2 pi times 6. So circumference equals 12 pi. So 12 pi is the full distance around the circle, but NQ is just what portion? A quarter of it. It's 1/4. If this were perfectly drawn out, obviously mine's a little off in the drawing, but if this were perfectly drawn out like it is in your books, you guys would see that it's a perfect fourth. So to find 1/4 of this, we're going to divide by 4. 12 divided by 4 is 3. So 3 pi, or in this case, we want to find the decimal because we're going to use it later to make things a little bit easier. So 3 pi, or about, using about symbols. So remember the squiggly equal signs represent about, 9.42. All right, so that is our circumference for, or not our circumference, sorry, that is our arc length for NQ. Now, for B, we want to find the area inside one of the sectors. So if we think about this sector right here, we want to find how much area that takes up in comparison to the whole circle. So we're dealing with area. So we're going to first find the area of the whole circle, then we can solve for the area of just that portion. So remember, our area formula is area equals pi r squared. So in this case, area equals pi 6 squared. 6 squared is 36, so our area equals 36 pi. Once again, we have 4 parts in this circle, so it's divided into fourths. So we're going to divide 36 by 4. 36 divided by 4 is 9 pi. So 9 pi is our answer on that one, and we can leave it in terms of the pi. Remember, leaving it in terms of the pi is a good idea. It makes things easier, and it's an exact answer rather than rounding, and we don't like to round. All right, now this last question we have to really think on. So we want to find the distance to walk this certain path. So we're going to start at P, so we're starting right here, and we're going to go to R. So R is our center. So we've got 6 so far. And then from R, we're going to go to Q. So another radius, which means another 6. And then from Q, we're going to go over to N. So we're going to go across our arc. So remember, we found the arc NQ. That's why I had us do the decimal. So it's going to be plus 9.42. And then from the end of arc NQ, back to P. So we're going to go this full length, so the whole diameter, which would be 12. So now we're going to take those 4 values and add them all together, and that'll give us that total walking distance, which ends up being 33.42. So there is our answer for that question. So when you're taking and dealing with arcs and finding distances, remember, if you have circles like these, think about how many portions it's cut into, and then you can find the circumference for the whole circle, and then you'll be able to solve for just the arc length rather than the arc degree. We're not looking at degrees on this one, we're looking at arc length. Length is the distance around rather than the degree of it. So there are 2 different terminologies with arc. Remember, arc is your key word for this lesson. All right, so if you guys have questions, do feel free to contact me during office hours. Let me know. Hopefully this won't be too bad for you guys. For the most part, I feel pretty comfortable with it. It's a lot of review stuff. There's a few new things in there, but hopefully you guys will be able to get it. Like I said, though, if you do get stuck, feel free to reach out. Send me an email, message me on Canvas. Email I'll probably see faster than Canvas, so by all means you can contact me that way. Otherwise, that is all. Those are your 3 lessons for this week that you have to worry about getting completed. Hopefully all goes well, and look forward to meeting with you guys this week. All right, doodles.